In this video, we're going to start to study the chapter 3 of the textbook. This chapter is devoted to the simplex method. In Theorem 2.7, we have seen that if a linear programming problem in standard form has an optimal solution, then it also has an optimal solution, which is a basic feasible solution. And the whole simplex method is based on this fact. In fact, it searches for an optimal solution only among the basic feasible solutions of the polyhedron. The main idea of the simplex method is to move from a basic feasible solution to the next along the edges of the feasible set, in such a way that the next basic feasible solution has always cost smaller than the previous one. This is our to-do list for this first part of chapter 3. First, we're going to present necessary and sufficient conditions for a feasible solution to be optimal. This is of fundamental importance because this allows us in the simplex method to know when we should stop because we have an optimal solution. Next, in section 3.2, we develop the whole simplex method. Then we discuss few different implementations of the simplex method. In particular, we will see the simplex tableau and the revised simplex method. In order to correctly estimate the number of operations performed by the different implementations, we also review section 1.6. Let's start with some notation that we will always be using in chapter 3. We will always consider standard form problems, and we are gonna always use the same notation. So our standard form problem is of the form minimize C transpose x subject to ax equal to b and x greater than or equal to 0. We will be using capital P to denote the corresponding polyhedron, namely the set of non-negative vectors x that satisfy ax equal to b. Also, we assume that the dimension of A is m times n, so we have m equality constraints and n variables. We also assume that the rows of A are linearly independent, and we've seen in section 2 why this can be done without loss of generality. We will also keep using our previous notation. In particular, capital AI is used to denote the ith column of the matrix A, and the AI transposed is the ith row of the matrix A. We are now ready to dive into optimality conditions. Now, many algorithms to solve optimization problems have a very similar structure. Namely, they are iterative, and at every iteration they have a feasible solution and they search for a better one. But they don't search for a better one among all the possible feasible solutions because that is too difficult, but they only search for a better solution in a neighborhood of such a solution. And this neighborhood is defined ad hoc based on the problem. So then the algorithm either finds a better solution in the neighborhood, and so it updates the current solution and it starts the next iteration of the algorithm, or it's unable to find a better solution in such a neighborhood. If this happens, then it means that the algorithm has found a locally optimal solution, where the concept of locally optimal, of course, depends on the defined neighborhood. Generally, a local optimal solution is not globally optimal. However, in linear programming, this is the case, so local optimality implies global optimality. In this section, we will follow a similar line of thought for linear programming problem, namely, and given a basic feasible solution to our linear programming problem, we will search for a direction of cost decrease in a specific neighborhood of our solution. This will lead us to the associated optimality conditions. So then the idea is to define a way to move from our current vector into some specific direction. And this is exactly what I want to formalize in this slide. So suppose that we are at a point x in P and we want to move from x in the direction of a vector d. Clearly our objective is to find a better feasible solution to our problem. So in particular, we want to move in a direction that keeps us inside the feasible set. For example, look at this picture here. In this case, our polyhedron is a quadrilateral in dimension 2. So let's say, for example, that our vector x is in the middle here. Then of course we can move in any direction, because if we pick any direction, we can always move in that direction and remain inside the feasible region. As long, of course, as we don't move too far. However, if we are, for example, in this point, which is on the boundary of our polyhedron, there are some directions that we shouldn't consider because they bring us immediately outside of the feasible set. For example, this happens if you go straight up from such a vector. In the picture, we have instead 4 directions that keep us inside the feasible region. And similarly here, now we have a vector x that is a basic feasible solution, and for example it doesn't make sense to move directly down because we would leave immediately the polyhedron. So this leads us to the definition of a feasible direction at a vector x, which formalizes the concept of a direction that makes sense for us to consider. Let x be a point in our polyhedron P. A vector d is said to be a feasible direction at x if there exists a positive scalar theta for which x plus theta d is still in P. So this definition means that from x you can move at least a little bit in the direction d while still remaining inside P. If we get back to our picture, for example, let's consider the vector x here, then these 3 arrows represent 3 possible vector d that are feasible direction at this point x. And the same thing happens if the vector x is here or here. The arrows are always feasible direction at that vector. Now we want to see what happens when we move along a feasible direction, starting from a basic feasible solution. Using our notation from chapter 2, we denote by b1 until bm the indices of the basic variables. And we denote by b the corresponding basis matrix with columns AB1 until ABM. At this point, we know how to write down our basic feasible solution. Namely, we know that for every non-basic variable, we have xi equal to 0, while the vector xb of the basic variables is given by capital B inverse times b. These are formulas that we've seen in chapter 2 and that will be fundamental throughout this chapter because we're gonna use them over and over again. So it's really important that you remember these formulas. Now that we've refreshed our memory on how a basic feasible solution x looks like, we are ready to move from x in the direction of d. So we're gonna consider vectors of the form x plus theta d for a positive value of theta. We want to consider a vector d that is a feasible direction. But not only that, we will see here that we consider very special feasible directions. This is simply our choice and the simplex algorithm will use only this type of choices. We want to choose a specific direction d which increases a specific non-basic variable xj from 0 to the positive value theta, while keeping all the remaining non-basic variables at 0. Algebraically, this means that we need to have dj equal to 1 and di equal to 0 for every non-basic index I different from j. So we have fully decided how the non-basic components of D should look like, but we haven't put any restriction on the basic components. Next, we will see that setting the non-basic components as we did directly forces the basic components to attain a specific value if we want the direction to be feasible. So let's then look at the basic variables corresponding to our vector x plus theta d. The corresponding subvector of basic variables is then xb plus theta db, where in db we have selected the basic components of the vector d. Since we want our direction to be feasible, we need to have that the new vector x plus theta d is feasible, and in particular it should satisfy all the equality constraints defining our polyhedron P. These equality constraints are then a times x plus theta d equal to b. We can expand the product and obtain ax plus theta ad equal to b, and we can then simplify this expression because we know that the original x was feasible, so ax is equal to b. So we're left with a theta ad equal to 0. So if we want the direction to be feasible, then theta ad should be equal to 0 for every theta positive and small enough. And this happens if and only if ad is equal to 0. So let's rewrite AD equal to 0 here, and let's expand AD according to the components of D. So AD is the sum of AI di for I that ranges from 1 to n, and now we break down this sum into the basic components of D and the non-basic ones. The basic components will be the sum for I that ranges from 1 to m of ABI dBi. And then the non-basic components are very simple because almost all are 0. The only non-basic component of D that is positive is dj, which is equal to 1. So we will obtain simply plus aj. Now the sum of the basic components can be written in the compact form capital B dB. So at the end of the day, we obtain that 0 is equal to B dB plus aj. At this point, we know aj, we know capital B, and we want to figure out dB. And we can use this system of equation to figure it out since capital B is invertible. So we can multiply this expression on the left by B inverse and obtain that dB is equal to minus B inverse times aj. And so this expression fully determines the basic components of the vector D. So essentially, so far, what we did is the following. We started from a basic feasible solution. We chose all the non-basic components of the direction D, and we saw that this choice, together with the feasibility of the direction, directly implies that dB should take exactly this form. The direction vector D that we constructed will be crucial throughout this chapter, and it will be called the jth basic direction, where, if you remember, j is the index of the non-basic variable that we want to increase. Let's see an example of a basic direction in the picture below. So let's say that we are, for example, in this basic feasible solution. This is the basic feasible solution where we have x1 equal to 0, x2 equal to 0, and we will have the remaining variables x3, x4, and x5 that will be some positive value. So our non-basic variables are x1 and x2. So we can look at the first basic direction and the second basic direction. In the first basic direction, we increase x1 while keeping x2 equal to 0. So the horizontal line is those of the point with x2 equal to 0. So we will be moving from x along such a line. But the question is, are we moving right or left? Well, in this vector, x1 is equal to 0. So going in one direction will decrease x1 and in the other it will increase it. But how can we understand which direction is which in the picture? Well, we can understand it from the position of the polyhedron P, which in this case is this gray area here. Remember that every point in the polyhedron satisfies x1 greater than or equal to 0. Therefore, x1 is positive on the right of the line x1 equal to 0 and negative on the left of the line. So our first basic direction consists in the vector that goes from our original basic feasible solution to the right along the line x2 equal to 0. It's a great exercise for you to think about every possible basic feasible solution in this picture and construct all the corresponding basic directions. Now that we've understood this example, let's get back to the general setting. The next question is our jth basic direction a feasible direction? What we definitely know is that if we go from x into this basic direction, then all the equality constraints are still satisfied. And they're still satisfied for any positive theta. However, in order for D to be a feasible direction, we also have to consider the non-negativity constraints. Once again, we consider separately basic and non-basic components. In fact, non-basic variables give us no problem at all, because they were all 0, and going in the direction D keeps almost all of them as 0, and one of them is increased to a positive value. Therefore, non-negativity constraints for all the non-basic variables will always be satisfied. So we only need to worry about the basic variables. And for basic variables, we need to distinguish two cases. The first case is, in a sense, the simpler one. Here we're assuming that X is a non-degenerate basic feasible solution. Since it's non-degenerate, we have that XB is a strictly positive. In this case, what happens to our basic components? Well, we saw the basic components are XB plus theta dB. And non-negativity on these variables means that this vector needs to be greater than or equal to 0. But now, since xb is strictly positive, then there always exists theta small enough for which this vector is greater than or equal to 0. So feasibility is maintained for theta small enough. This directly implies that D is a feasible direction. So in the first case, if X is a non-degenerate basic feasible solution, D is always a feasible direction. We can now visualize this case in our example, and we can reuse the example of a basic direction that we saw earlier. In fact, let's consider this basic feasible solution, and let's consider the first basic direction. In this case, as we already discussed, we're moving from this vertex to the right along the line x2 equal to 0. As you can see from the picture, this is a feasible direction. And this is simply because all the basic variables x3, x4, and x5 are strictly positive at this basic feasible solution. So informally, in order to violate any of them going in this direction, we need to travel a positive distance. Unfortunately, things don't go as nicely in the case where X is a degenerate basic feasible solution. In fact, in this case, it might happen that D is not a feasible direction. And so how can it happen that for a basic component, as soon as we have a positive theta, we violate the corresponding non-negativity constraint? Well, it must happen that this basic component of the original vector x was equal to 0, and the direction vector in the same component is strictly negative. In this case, following the jth basic direction, the non-negativity constraint for the variable xbi is immediately violated for any positive theta. This means we are led to infeasible solutions, and so the direction vector d is not feasible. Let's see an example of this behavior. In our example, the vector f is the only degenerate basic feasible solution, so we will pick our vector x to be exactly f. Now I need to specify to you the basic variables and the non-basic variables because there are multiple choices that give me the same basic feasible solution f. So I want to pick as non-basic variables x5 and x3. Clearly, f is the corresponding basic feasible solution because it is at the intersection of the two lines x3 equal to 0 and x5 equal to 0. Now let's look at the third basic direction. In the third basic direction, we want to keep x5 equal to 0 and increase x3. So from here, we're going along the line x5 equal to 0 in the direction right. So we're going in this direction. But you can see that as soon as we move away from f, we become immediately infeasible, so this is not a feasible direction. Note that if instead we looked at the fifth basic direction, then we would have moved along the line x3 equal to 0, so along this line, and in the direction left, so from f in this direction to the left. And you can see that this is instead a feasible direction. Now that we've understood the basic directions, I want to shift our focus to the cost change along such a direction. In fact, the reason we're moving away from a vector x along a direction d is to find a better vector, meaning a feasible vector with a better cost. So we're interested in the cost change, namely the cost of the new vector minus the cost of the old vector. Algebraically, this is C transpose x plus theta d minus C transpose x. Of course, C transpose x simplifies and we're left with the theta C transpose d. So this means that the cost changes linearly with theta. The more we move in the direction d, the more the cost will change. So we want to focus on the rate of cost change, which is the cost change along that direction if we set theta equal to 1. And this is exactly C transpose d. Now we can use our knowledge of the algebraic expression of d to figure out exactly what is this number C transpose d. Once again, the first thing we want to do is break down this scalar product in its component. So this is the sum for I that ranges from 1 to n of Ci di. Again, we consider separately basic components and non-basic components. Basic components give me the sum for I from 1 to m of Cbi dvi, and the non-basic components give me simply Cj, because dj is equal to 1 and all the other non-basic di's are equal to 0. Similarly to what we did before, we now write in a compact way all the basic components and we obtain Cb transpose dB plus Cj. And now we substitute the algebraic expression of dB that we figured out a few slides ago and obtain that this is equal to Cj minus Cb B inverse Aj. Once again, in this expression, we used the subscript capital B to indicate the subvector of C containing only the basic components. So how can we interpret this formula for the rate of cost change? Cj clearly corresponds to the non-basic variable xj that we are increasing from 0 to 1. So Cj is the cost per unit increase in the variable xj. And the remaining part of this formula, this minus Cb transpose B inverse Aj, is simply the cost of the change in the basic variables which is needed in order for the vector x plus theta d to satisfy the constraints Ax equal to b. This rate of cost change along a basic direction is clearly a fundamental quantity. And this is because it makes sense to go along this direction only if this value is negative, because this means that it will lead to solutions with lower cost. This quantity is in fact so important that it deserves a definition of its own, and it's called the reduced cost, and it will be denoted by C bar j. Let's read through this definition. Let X be a basic solution, let capital B be an associated basis matrix, and let Cb be the vector of costs of the basic variables. For every j, we define the reduced cost C bar j of the variable xj by C bar j equal Cj minus Cb transpose B inverse Aj. This definition, of course, is not surprising because this is the formula that we just computed in the previous slide. However, there is a little detail that should confuse you at this point. In fact, in the previous slide, when we computed this quantity, the variable xj was non-basic. And all the discussion that led us to this formula doesn't really make sense if we consider instead a basic variable. The fact that we are defining here the reduced cost also in the case where an xj is basic is simply a technicality, and we will discuss this very soon. But before that, let's look at an example. Here we consider the linear programming problem where we minimize a general objective function sum of the Ci for I that ranges from 1 to 4. Our constraints are sum of the xi's equal to 2 and then 2x2 plus 3x3 plus 4x4 equal to 2 and then non-negativity constraints. So this problem is in standard form as it should be. Let's look at the first two columns of the constraint matrix A. We have 1, 2 for variable x1 and 1, 0 for variable x2. Here they are, A1 and A2. These two vectors are linearly independent, so we can choose x1 and x2 as our basic variables. So our basis matrix has the first column equal to A1 and the second equal to A2. Let's then obtain the corresponding basic solution. We're setting x3 and x4 to 0 because they are our non-basic variables, and then we have to solve the system of equations for x1 and x2. If you do this, you obtain x1 equal to 1 and x2 equal to 1. So our basic solution is a 1, 1, 0, 0. It is non-negative, so it's a basic feasible solution. Also, since our basic components are strictly positive, it is non-degenerate. Since the non-basic variables are x3 and x4, we could construct the third or fourth basic direction. In this example, we construct the third basic direction d. So how do we construct it? We set d3 equal to 1 because the third basic direction, and so d4 equal to 0. Now we can use our formula to obtain the subvector dB of the basic components, which are in this case d1, d2. The formula that you should remember is dB equal to minus B inverse Aj. So we have d1, d2 equal minus B inverse times A3. We have already written the matrix capital B earlier, and if you compute the inverse, you obtain this matrix over here. Then the vector A3 is the third column of the matrix A, which is 1, 3. And here it is. If you compute then the product, you obtain minus 3 halves, 1 halves. So we now know the third basic direction, which is the vector D equal to minus 3 half, 1 half, 1, 0. Here it is. We can also compute the rate of cost change along this basic direction. We can compute this rate of cost change in different ways. We can use the definition of reduced cost, or we can simply use C transpose D, which was the starting point that allowed us to come up with the definition of reduced cost. In this case, we have already computed D, so it's quicker to compute the rate of cost change by computing C transpose D. This scalar product gives you minus 3 half C1 plus 1 half C2 plus C3. If you write down the formula for the reduced cost of the variable x3, you will obtain the same result. As promised, we now get back to the technicality that we have in the definition of reduced cost, namely the fact that the reduced cost C bar j is defined also for the case of a basic variable, namely when j is equal to b of I for some index I in 1 to m. What we will show is that in this case, the reduced cost will be always 0. Everything we have to do is to compute explicitly this quantity under the assumption that j is equal to b of I. The main trick in this argument consists in understanding exactly what is the product B inverse AJ. Now the columns of the matrix B are AB1 until ABM. So then the product B inverse times the matrix with columns AB1, ABM is equal to the identity, just because this big matrix is simply B. So then what can we say about the product B inverse AB of I? B inverse is the same B inverse that we have here, and ABI is the ith column in this big matrix. So this product is simply the ith column of this product. Therefore, it's the ith column of the identity matrix. So it is the unit vector EI. Now the product B inverse ABI is exactly what we needed to compute here under the assumption that J is equal to B of I. So we can now write the reduced cost of the index B of I. Here it is. Using the formula, this is CBI minus CB transpose B inverse ABI. We now use that B inverse ABI is simply equal to EI, and we obtain that this reduced cost is just CBI minus CB transpose EI. Now CB transpose EI is just a component B of I of the vector C. So we obtain CBI minus CBI, which of course is 0. So we have shown that the reduced cost of every basic variable is 0. So all in all, the definition of reduced cost was also given for basic variables. While not really needed, this will make our life simpler later on, as long as we remember that for basic variables, the reduced cost is always 0. We're finally ready to give the main theorem of this video, which provides us with optimality conditions. And most of this statement is very intuitive, given our interpretation of the reduced costs as rates of cost change along the basic directions. Consider a basic feasible solution X associated with a basis matrix B, and let C bar be the corresponding vector of reduced costs. Then, if C bar is greater than or equal to 0, then X is optimal. Vice versa, if X is optimal and non-degenerate, then C bar is greater than or equal to 0. The first thing that you should notice is that these two implications are almost an if and only if. In fact, if we didn't have this and non-degenerate, then it would be an if and only if. Namely, it would be X is optimal if and only if C bar is greater than or equal to 0. Unfortunately, this is not the case because, as always, degeneracy may mess things up. Later on, we're going to discuss much more this statement, but let's first prove it. For the proof, it will be useful to consider the contrapositive of the statement B. Such a contrapositive is if C bar is negative, then X is degenerate or not optimal. Here it is. I'm gonna call this B prime. Now let's prove our optimality conditions. So here we have the statement of theorem 3.1 again, where I've already replaced B with the contrapositive B prime. Let's start with showing A. So we assume that C bar is greater than or equal to 0, and we want to show that X is optimal. So how are we going to show it? We show C transpose X less than or equal to C transpose Y for every Y feasible. This happens if and only if C transpose D is greater than or equal to 0, as long as we define D as Y minus X. So this is just for notation simplicity. The first thing that I want to do is write dB, so the basic components of the direction vector, in terms of the non-basic components. So let me first introduce the notation for the non-basic indices of x. Let capital N, as usual, be the set of non-basic indices of x. So first we write dB in terms of the di with I in n. In order to do this, we essentially need to observe that AD is equal to 0. So why is AD equal to 0? AD is equal, by definition of D, to AY minus AX. Now both X and Y are feasible by assumption, so this is equal to B minus B, and so it's 0. Now we rewrite AD equal to 0 by dividing, as always, basic and non-basic components. We obtain B dB plus the sum of AI di equal to 0, where the sum ranges over all the non-basic indices. Since B is invertible, this allows us to write dB in terms of the remaining quantities. So we obtain that dB is equal to minus the sum for I in n of B inverse AI di. Having written dB in this way allows us to finally be able to consider C transpose D, which is our target. So we have C transpose D equal to, again we divide basic and non-basic components, C, B, dB, plus the sum of Ci di for I in n. We can now substitute dB and obtain equal to minus the sum for I in n of C transpose B, B inverse AI di plus sum of I in n Ci di, which remains unchanged. Now di appears in both sums, so we can write this as the sum for I in n of Ci minus Cb transpose B inverse AI times di. And now we recognize inside the parentheses our definition of reduced costs. So this is simply the sum over I in n of C bar I di. Now let's expand di using its definition. This is the sum over I in n of C bar I times yi minus xi. At this point xi is equal to 0 because I is a non-basic index, and yi is greater than or equal to 0 because of the feasibility of y. By assumption, we have that C bar is greater than or equal to 0, and now yi minus xi is greater than or equal to 0. Therefore, this whole sum is greater than or equal to 0. And this concludes the proof of point A. So now let's prove B prime. which is equivalent to the original b. So we need to assume that c bar j is negative for some j, and we want to show that x is degenerate or not optimal. So let's go to the next page. Suppose c bar j is negative for some j. Now, if x is degenerate, we are done. Thus, we now suppose that x is non-degenerate. Now we know that the reduced cost of basic variables is always 0. And since this reduced cost is strictly negative, so it's not 0, we argue that xj is non-basic. So let me write it. Since the reduced cost of basic variables is 0, xj is non-basic. Therefore, c bar j is the rate of cost change along the jth basic direction. Now, because of non-degeneracy, this is a feasible direction. So since x is non-degenerate, the jth basic direction is a feasible direction. And it is of cost decrease, since c bar j is strictly negative. So we know that by moving in that direction, we obtain feasible solution with cost less than that of x. And this immediately implies that x is not optimal. And this concludes the proof. So let me write this last argument. By moving in that direction, we obtain feasible solutions whose cost is less than that of x. And x is not optimal. And so this concludes the proof of our optimality conditions. Let's get back to the slides. Now that we have shown theorem 3.1, as promised, I want to discuss a little bit more the statement. So in this next slide, we have once again the statement of theorem 3.1, and I want to consider separately what can happen in the non-degenerate or in the degenerate case. The reason we don't have an if and only if in this theorem is that we could have an optimal solution with the c bar j strictly negative for some non-basic index j. If this happens, clearly it must be the case that x is degenerate. If instead we consider the case when x is non-degenerate, then we do have an if and only if, namely the vector x is optimal if and only if c bar is greater than or equal to 0. So we can check if x is optimal by just looking at the reduced costs of the non-basic indices, which is the same as examining the n-m basic directions. If our basic feasible solution x is degenerate, We don't have such a simple way to determine whether x is optimal or not. But fortunately, the simplex method will manage to get around this difficulty. If we use theorem 3.1 to argue that a solution is optimal, we need to satisfy two conditions, namely feasibility and non-negativity of the reduced costs. Now we know how to write feasibility and the reduced costs in terms of our basis matrix B. So this naturally brings us to the definition of a basis being optimal. So a basis matrix capital B is said to be optimal if capital B inverse B is greater than or equal to 0, and this is exactly feasibility of the corresponding solution, because if you remember, capital B inverse B is the vector of the basic components of our basic solution. The second condition is non-negativity of the reduced costs, which is C bar transpose greater than or equal to 0. And we've already seen that C bar can be written as C transpose minus CB B inverse A. So then you see this gives us a definition of a basis matrix to be optimal. And in this definition, essentially, we don't even need to talk explicitly about the corresponding basic solution. So now, what is the connection between an optimal basis and an optimal basic solution? If we have an optimal basis, then the corresponding basic solution is feasible because of A, and it satisfies the optimality conditions thanks to B, and therefore it is an optimal basic feasible solution. So essentially, if we have an optimal basis, we also have an optimal basic feasible solution. But the reverse direction is not always true. In fact, it can happen that we have a basis that is not optimal, but the corresponding basic solution is optimal. The only way this can happen, from our theorem 3.1, is that at least one reduced cost is negative. Therefore, this can only happen when the basic solution is degenerate. And with this, we end our lecture on optimality conditions. Now we are ready to develop the simplex method, and we're gonna do this in the next lecture.